welcome to the session. Greeting of the day. We are in the discussions of solid state sensors. In this solid state devices, we have first seen about the silicon, intrinsic semiconductors, extrinsic semiconductors, right? And then also we have seen about the N-type, P-type, then the transistors, PN junctions. We are in the lattice. So from the transistor, I am dividing into two categories of bijunction transistors. Their PNP, NPN I have divided. We have seen these things in the last class. And later in continuous with it, in today's class, we are going to see about this field effective transistors. There I am dividing again into JFET and MOSFET. This we are going to do in this class. See, previously we have done, we know the electron flow should be made from emitter to the collector. So we have three devices, three terminals of emitter, collector and the base. In the similar pattern, here also electron flow should happen in the FET also, in the JFET also, in the MOSFET also. So I am doing here also, I am naming it the source, the drain and the substrate, and the gate. Okay, the substrate is connected to there. So here also having the 4 components, as like here we have there 4. Okay. For FET, we have 3 terminals of number 1 source, number 2 as a drain, number 3 as a gate. So what we have did here, we have taken maybe a PNP junctions or maybe a NPN junctions. We have made the supply to be connect, the electrons to be transferred from source to gate, source to drain. But as like in transistor, we have used the base, we have used here the gate for the increasing, decreasing, voltage pushing or downwards. Right? For those cases, we are using the gate operations here. There we have did the current operation, flow of current has been controlled by the base. Here we are going to control the voltage by using the gate operations. That we will see one by one. The source, number 1, the terminal through which the majority charge carries the electrons, carries the entire channel and is designated as Ig. And the drain I am talking, the terminal through which the majority charge carriers leaves the channel and designated as Id. So now we want to concentrate it. So what I am telling, from the source to drain, it is traveling. It means from here, it is source. At the bottom I have written as a source. This is source. This is a source. At the top we have drain. Okay? The electron flow, it should be happen from this direction. It should happen from this end to that end. This is a separate circuit. The source to drain is a separate circuit. And in the middle we have the drain to boost, to reduce. As like a transistor, like a base we have added, here we have having the gating system. So we will tell. There are 2 internally connected heavily doped. There are two internally connected heavily doped impurities region formed by alloying by diffusion to create a PN junction. To create a PN junctions, these impurities regions are called as a gate G. And what I have did, please carefully listen. We have here also the formation of, PNP circuits. I have P and P I have taken. This we can tell like this zones. Here we have a P and N zone are formed. See, this zone is N zone and that zone is PA. So here also one PN junction is formed. 2 PN junctions are formed. One on the left side, one on the right side. We have a gate connection here. like a base connection here also and here also. So there are two PN junctions can be formed from this PNP configurations. That is what I have mentioned there. There are two PN junctions are formed in this. A voltage VGS is applied between the gate and the source. What I am going to do here, I am going to apply a voltage signal from here to this connection. This is, we are naming this as a gate source. This is gate, this is source. Voltage applying from gate to source. This is going to alter the depletion zone formation between P and N. Right? Right. What is the channel? The last one. The region between the source and the drain is sandwiched between the two gates. Sandwiched between the two gates. So here you see in this image, please understand. Here we have the source. We know this is the source region, and this is the drain region, and we have formed PNP between this gating system. So here the PNP is formed. The channel, the plate between this N is generated around this. We have doped here. We have doped the P here. Similarly, we have doped the P on the N. We have taken one N channel on that. In this side, this side I have doped a P, and similarly on that side I have doped one more P. Right? So it become like this. So it become like this. So I am calling this part, I am calling this region the connection, this region the connection, here also the connection, here also the connection. So I am calling this region as a source, this region is drain. The electron flow should go from here to here, and when the circuit is connected. But I am controlling this circuit with respect to two gating system in between that, sandwiched. Okay, so this is I am naming as a G. So that is what here mentioned. The region between the source and drain. The region between the source and the drain. This entire region is called as channel. Okay, sandwiched between the two gates. Sandwiched between the two gates. This gate and this gate, which already doping happens. Called as, and the majority carriers move from source to drain through this channel. So majority charge carriers move from source to drain through this N channel. Okay. So the FET is a 3-terminal device that is constructed with two PN junctions. Now we know two PN junctions. Here one PN junction, and this side one PN junction is formed. It means at center we have N, P, N. And that side also we have P doped N, P. So two PN junctions or two NP junctions are formed there. We are going to use that. So now that is what it is classified. Two basic classifications of a field effective transistor is N channel FET, P channel FET. It may be the channel what we have chosen, the center one. The channel what we have chosen may be N channel, or otherwise the channel what we have chosen may be P channel. If it is N channel, we are going to dope with respect to P at the both ends, and it becomes PNP. If it is P channel, I am doping with respect to N. It means N type extensive impurities. Okay. So here I am going to dope with N. So the combination we can able to do here. Right. The direction of arrow at the gate indicates the direction in which the gate current flows when the gate junction is forward bias. I told you in the transistor, in the reverse bias, our depletion zone become extended. In the forward bias, repulsion happens and pushes inside, and therefore flow of current happens one end to other end, so it cycles generated. So what happens? Therefore, we should consider the forward bias only for the flow of current. So when it is in forward bias, what is the arrow condition? N channel, the arrow at the gate junction points into the device. So here from the gate, this is the symbol. I am talking about the symbol. Okay. So likewise the symbol will be there. So we have to draw gate, we have to put gate, drain and the source. We have to put the arrow inside. Similarly for that, you have to put the arrow outside the gate. Okay, it's simple. This I reconnect there from the transistor. So this is the emitter, collector and the base. For N channel, NPN junctions, the arrow from the base to emitter I have given. Okay. Similarly here, the gate to source I have given. For the P, emitter to base, it's going outside. It means it's going outside. Okay, don't confuse. Now, listen carefully, now the concept we are coming. FET controls the flow of current. FET controls the flow of current. FET controls the flow of current by varying the voltage. Therefore, it is called as a voltage varying device. It is also called as a, this FET is also called as voltage varying device. In transistor, we have controlled the base current, the battery, positive, negative. Therefore, the flow of current monitored. Here we are going to do a voltage differences. We are going to reduce or increase. Therefore, this flow of current is again monitored. Anyhow, the flow of current is monitored, but varying the voltage here. Voltage which is in the gate connection, which in turn alters the conductivity between drain and the source. What I am telling, please listen. So this is the connection. We know we have P and the N channel and then again the P. What I am doing, the flow of current should takes place from source to the drain, that we know now. But now I want to control the flow of current to be stopped as a switch, to be increased, to be decreased. What I am doing, I am supplying a voltage from the gating system and the source. Voltage of gate and the source I am doing. So in this region I have formed a PN junction, P and N. So this is the N. N having the one side, here have the source. So this I have connected. So what it become? What it become? You see, this become like this. Let us consider this PN region like this. So in this case, we have P here, we have N here. Okay. Therefore, when I am connecting this at center, we have a depletion zone. See, at center we have a depletion zone here. Okay, the depletion zone is there. We are understanding. Okay, now when this current flow takes place, when we are giving a voltage greater than 0.7, but that is also in the forward bias, then only the repulsion takes place inside. But I am not doing that. What I am doing, instead of positive, I am giving the minus here. Right? So similarly, this side I am giving the positive here. Opposite connections I am giving, reverse bias I am giving. So what happens? This depletion zone increases. This depletion zone keep on increasing. So the depletion zone keep on increasing. So what happens then? If the depletion zone is increasing, now we come here. Now the same concept we are applying. This dotted line belongs to depletion zone. There is a N, there is a P. I am applying the negative. See, it is visible. It is a negative, and I have given there. What happens? This negative increases the depletion zone between N and P. So this is, let us consider, less voltage is applied. Therefore, the depletion zone also very less. And that is what I have written with a small negative gate source voltage. This is negative. Reverse I have given. Reverse bias I have done here. So next, I am increasing the negative because I am attracting more. This side it's attracted, then this side. Electrons are moved this side. The electrons are moved this side. Therefore, here already there is no electrons to jump from here to here, not happening. Okay, therefore what happens? With the high negative gate source voltage, I am increasing. It means this dotted lines belong to depletion. I am writing here, okay? This belongs to depletion. Okay? When the negative is increased more, it attracted towards the corner, therefore the connection between N and the P, it increases, the depletion zone increases. I am talking about this point. Okay? If it is increasing at the both ends, the depletion is become more. Therefore, This is the point. From the source to the drain, flow of electrons or flow of current, it stopped. So here the yellow color represents the flow. Depletion zone is less, reverse bias, the flow of current happens from source to drain. But I have controlled the flow of current by using the increased VGS. Here, similarly. Now, again, with a small negative gate source, and these both are same. These both are same. Right? Again, I have decreased. Again, I have decreased. This negative has been decreased. Now, what happens? The depletion zone, if it is strong, if the depletion we are giving a high negative, depletion increases. Less negative, depletion zone reduces. Okay, this depletion zone is reduced from P to N. This region I am talking. This is P, this is N. In between few other parts are found. This zone, see, this zone is depletion. Here we have N. Two zones are there. Similarly, that side also two zones are there. Here also. I think you understand. Okay. So now again with the small negative, the depletion zone has been reduced. It will go on this side. It went to this side. Therefore, we have got the space. The N channel is cleared. Therefore, we can able to easily pass the current from the source to the drain. So what we have done? We have controlled the voltage. Therefore, by controlling the voltage, the flow of current also controlled by increasing the depletion, decreasing the depletion zones. This you should remember. Here we have found two PN junctions, one in the left, one on the right side. Right. For example, I have taken a tap for this FET. I have taken a tap here. Right. So I want to make a water should come from top tank. Come from the tank to the drain. Okay. So let us consider. It means this is the source. From the source to the drain it should come. Where we are controlling these cases, we are controlling through the gate. It means this opening closing is a gate. Now just I am comparing here. The water, the electron flow should take place from where the cause of water flow is the difference between the tank and the tap. From the tank to tap through the down. Cause of electron flow is applied voltage between source and drain. We are applying the source and voltage here to here, here to here. Therefore, the flow takes place. Here for water controlling which one? The valve knob. We are controlling through the valve knob. There we are controlling through the drain actions, the gate actions we are doing there. Through the gate actions, it can be controlled. Here the sink, which one? It goes to sink. For these cases, the bottom is a sink. We are naming, just for example, we are naming a sink. But for these cases, it goes from source to drain. What is a tap opening? It is a tap opening as a source. Here it is a source. It should go from source to drain and controlled by the gating system. Okay, very simple. Transistor, we have a base. Here, in this we have a gating system. So for this, we have already by the diagram, I have divided like this. Right? FET is converted into N channel FET, P channel FET. What is this? This is channel at the center to be N channel, the main one. Let's see this one. This is the N channel FET. I am changing this N to P. I am changing this N to P. So again, this doping become N. This become N. And all the circuits are reverse polarized. So here for P, I am giving negative. V, G, S is negative. See this one negative. For this one, here it is N. I want to give positive. So I have given positive. So this is a difference. We have to draw that main diagram and this is two. N channel FET, P channel FET. Through which one it happens? Electric field it happens. Through, you see, it happens through electric field. It generates the field here. It generates the electric field. Depletion zone happens through the electric field. Therefore, it is called as a. Okay, now you see, we move to the next one. of applications of this FET. So the FET is used as I have mentioned earlierly. It will be useful in creating as a switch, like amplifying or like a buffering actions, like a on and off actions you can able to do in this FET. So now I am coming to the next one of MOSFET. So how I am dividing? We know this is we have divided from here the FET. It means that from the transistor we came down. Okay, BJT bipolar junctions we came from the FET. From FET we have done this N channel and P channel. The center part to be N, the doping to be other two. So likewise we have the N here doped with P, here doped with P. In case this is P channel means P doped with N, here also doped with N. Likewise we have did this FET. In MOSFET also the same method of gate, source, drain are there. But here I am dividing again into enhancement MOSFET, depletion MOSFET. The simple concepts we will understand. Here also the similarly the N channel MOSFET, P channel MOSFET, N channel depletion MOSFET, P channel depletion MOSFET. So enhancement means N channel enhancement MOSFET and P channel enhancement MOSFET. N channel depletion MOSFET, P channel depletion MOSFET we have to see. This categories now we have to see. Before going there, we should understand here also similar pattern of a source, drain and gate are there. So similarly this substrate. What I have did in this image, you see, the source has been directly connected. Please see carefully. The source has been directly connected to the N channel, right? And here the drain also has been directly connected to the one more N channel. And the substrate here, the blue color substrate here is at the center, and it is not connected to the gate, and it is insulated in between by this yellow color insulator, silicon dioxide insulator we have used. So source directly connected to N, drain directly connected to N, and the gate is not directly connected to the substrate. It means see this wire is connected here. We have the connection here. It means we have the connection. We have the connection here. We have the connection here. But we have not having the connection. It is insulated. Please keep remember. The gate contact is insulated from the gate contact. The gate contact is insulated from P-type substrate using a silicon dioxide insulator. That is what I told you. This is not in contact. This around this point. Okay. Please remember. We come there back. Source contact are directly in contact with N-type. Again, the drain contacts are directly in contact with N-type. These two are in connection. These two are in connection. Substrate will always be connected to the source terminal. Hence, it is MOSFET operated through 3 terminals. This we have connection here. This we have touch up here. Therefore, it is being generally named it as a. We are not considering the substrate. We are naming it as a 3 terminal device: source, drain, and the gate. Okay. Likewise, we consider. The operation, the DC voltage source is connected towards the 2 N-type regions. So we are connecting the supply of 2 N-type regions. We are connected to the battery of a DC power supplies we have given. So here we have given N, and here we have given N. The electrons should flow between these two. That is the idea. Okay. First transistor we have used base. Again we have used the gating system. In the FET, here also the same, the gate is there. The gate we are going to use, but how we should see. Okay, one channel terminal is connected to the positive terminal of the drain. One N terminal is connected to the positive, one N terminal to the negative. So 1 and 1. One is connected to the positive, one is connected to the negative. So we have done, source and drain are connected. How we have done? We remembering that this N is connected to the negative. N to N it is forward bias. We naming this as a forward bias. And similarly N to N is naming this as a reverse bias combinations. We are naming this as a reverse bias combinations. Here positive to N it is reverse bias. N to minus it is a forward bias combinations. After connecting we get two PN junctions. After connecting we are getting two PN junctions. How we are getting two PN junctions? See, this one combination is one PN junction and this combination is belong to the second one. So one between N-type drain and P-type substrate. That is what I am telling. The first one between N-type drain and the substrate, and the second one between the N-type terminals and the also the substrate. So we are getting two NP junctions here. We understand these things. So later you see the operations, no flow of current between the source to drain. No flow of current between source to drain. There is no chance of supplying N to N. Here it is not going because the P is that the depletion zone is there in between these things. We have to remove those things. How we are doing to make so how we are doing, one positive terminal is connected to the gate source. One positive terminal is connected to the gate source. So for this gate source I am giving the positive connection. Already N to N it is a negative forward bias I have given. It is going to push. It is going to ripple there inside inward side. Okay. So that one I am attracting. So I am giving a positive connection at the gate. So what happens? This substrate having some electrons. These electrons are attracted by the positive. Here it is positive. It means here it is positive. It means you see this zone is positive. So these electrons will attracted here towards there. If it is attracted here, we have insulator. This is insulator. This is insulator. Okay. It cannot cross and it cannot flow, but it is accumulated. It is accumulated here this point. So it is accumulated there. If it is accumulating, what happens? Already N having electrons. Here also the positive attracts electrons. These electrons are accumulated here. This creates one channel. This creates one channel between these two N channels. So with respect to this, we can able to travel here. With respect to this, we can able to travel. Okay. This with respect to this, we can able to travel here. Okay. We achieved. Okay. The minority electrons of the p-type substrate accumulated towards the gate region. That accumulated totally based on how it is. It cannot cross. We know it is insulated. The accumulation totally based on which one? How much the gate voltage is applied. This how much we are applying. This voltage how much we are applying. It is based on that. If it is high, it attract more. If it is less, it will. If it is less, it will attract less. We need more to flow. If it is less, like acting as a switch, it will reflect. The supply will be off. If it is increasing, it will flow will takes place. This accumulation free electrons will act as a N type. So here also one N is generated. Here also now one N is generated. N it will automatically the cycle will flow. Very easy. So therefore this accumulated free electrons will act as a N-type semiconductor. Therefore I am concluding this increasing of applied voltage increases the conduction. Increasing voltage, increase conduction. Voltage terminating, conduction not there. This become again it is become empty. So this is greater the conductance between the source and the drain. So where we are understanding. So I am increasing this thing. So the conduction happens between source and the drain. So I am reducing this. Now I am reducing this. This is terminated. No conduction. I am increasing this. It is induced. It is an induced channel. Okay, that is what I am written here. This is a induced channel. This point is induced channel. If it is induced, it goes. If it is not induced, it won't go. It is depend upon increasing voltage or decreasing voltage. So that is what I simply have mentioned as a threshold voltage here. The greater the applied voltage on positive terminal, greater the conductance. Gate voltage is less than the threshold voltage. We are fixing on voltage, how much we have to give. you know, if you are giving it to run, conduction happens. If you are not giving, how much we have to give? 0.7 greater than 0.9, 1, how much? If gate voltage is less than threshold voltage, this we have to decide. Okay, it's off mode. Gate voltage is greater than threshold voltage, it is in the on mode. So this is MOSFET act as a gate control switching device. Therefore, it is a switching device. So simple. Now I come to the end. N-channel depletion MOSFET, N-channel enhancement MOSFET. What's the comparison here? If the gate voltage is negative, please listen carefully. If the gate voltage is negative, positive holes are accumulated. If it is negative, if in case I am putting negative, it attracts here the positive. See, like this it attracted. If it is positive, this N-channel won't conduct. If it is negative, it attracted positive here. It attracted positive here. There is no conduction takes place. So it is a depletion MOSFET. We have to enhance. I am doing. If the gate voltage is positive, the gate voltage is positive, negative electrons are accumulated. So current flow is made on mode. This is off mode. This is the on mode. So this all things happen for P-type N channels. So all things happen for N channels. Now I am going for P channel. In case I am putting P channel here, it's used to source and drain. Then similarly we can go for P channel enhancement MOSFET. Similarly we can go for P channel depletion MOSFET. What I have did here, see, I have created these two ends, this N and the P. This I call as N channel MOSFET. Maybe an enhancement, or maybe a depletion mode. So again I am creating here, instead of N I am putting P. I am putting P here. Okay, this is P channel MOSFET. Okay, this may be a enhancement, this may be a depletion mode of actions. So in this class we have seen about on the semiconductor, we have seen about here the FET, and here we have divided into N channel and P channel FETs. And similarly, and also we have divided the same thing into, FET is divided again into MOSFET, and this again we have divided into N channel, so we can write as enhancement and depletions MOSFET. The remaining part of the subject we'll see you in the next session. Thank you.
Let us discuss MOSFET in detail. MOSFET is an electronic device most widely used in ICs. It has three terminals named as source, drain, and gate. Construction of basic design of MOSFET is quite simple. Just take a block of P-type semiconductor. This block will be your base for MOSFET. We also call it as substrate, and the entire MOSFET we will fabricate on this base. Now two portions on the same side of this P-type substrate are made highly doped with N-type impurity, as these are shown here in the figure. Source and drain terminals are brought out from these two N regions as shown. Now, the entire surface of the substrate is coated with a layer of silicon dioxide. Silicon dioxide will behave here as insulation. On this layer of silicon dioxide, a thin metallic plate is placed. This metallic plate will act as gate contact to the substrate. The gate terminal is brought out from this metallic plate. Hence it is seen from the figure that gate contact is insulated from the substrate, but drain and source contacts are directly connected to respective N-type regions. This was the constructional feature of a MOSFET. Now we will come to the operational features of MOSFET. For that, we have to connect on DC voltage source between these two N-type regions. The N-type region connected with positive terminal of the source is called as drain, and the N region connected with negative terminal of the source is called as source. As soon as the drain and source are connected with DC voltage source, there will be two PN junctions formed. One is in between N-type drain and P-type base, and the other is in between P-type base and N-type source. As drain is connected with positive terminal of the source, the drain is in higher voltage than base. Hence, this PN junction is reverse biased. On the other hand, as source is connected with negative terminal of the battery, P-type base will be at higher potential than N-type source. Hence, this PN junction is forward biased. As between drain and source, there will be one reverse biased and one forward biased junction. There will be no significant current flowing from the drain to source, but a tiny current continues to flow due to minority carriers. We can say that virtually there is no continuous path or channel between drain and source. Now let us see what happens if one suitable positive voltage is applied at gate terminal of the device. In that case, due to attraction or positive potential of gate contact plate, negative free electrons, that is minority carriers in P-type base, will be accumulated towards a contact plate and form a channel of negative charge carriers even inside P-type semiconductor. This channel, due to higher concentration of free electrons, will behave as N-type semiconductor, although entire base is doped with P-type or trivalent impurity. It is obvious that the number of free electrons accumulated towards gate contact plate depends on the strength of positive potential given to the gate terminal. Hence, width of N channel depends on the voltage applied at gate terminal. More the applied voltage, greater the width of the channel, means greater the conductance between drain and source. Here we have seen that there is no direct connection between gate contact and substrate. Instead, these are insulated from each other. But due to electrostatic attraction, the conducting channel between drain and source is formed, and because of that, the channel is also called induced channel, and the device is called induced channel MOSFET. It is also clear that when there is no voltage applied to the gate of the device, there will be no current from drain to source, except negligible amount of saturation current due to minority carriers. But if the gate voltage is gradually increased by keeping fixed drain to source voltage after certain minimum applied gate voltage, drain to source current will start flowing. And this voltage is called threshold voltage. So, below threshold voltage, the device will behave as non-conducting or in off mode. And for gate voltage greater than threshold value, the device will be in conducting or on mode. So this type of MOSFET is suitably used as a gate control switching device. Let us discuss about depletion MOSFET. For understanding depletion MOSFET, we try first to get a basic idea about enhancement MOSFET. In MOSFET, there are two highly doped N regions on one side of a P-type substrate. These two N regions behave as drain and source respectively. There is no previously created N channel between drain and source. The entire surface is coated with silicon dioxide layer as insulation. The gate contact in form of the metallic plate is placed on the silicon dioxide layer. The gate terminal is projected on the gate contact plate as shown. Now, if a voltage source is connected across drain and source terminal with positive terminal at drain and negative terminal at source, there will be no current flowing from drain to source, as there is no conducting channel between drain and source. Moreover, due to applied positive voltage at drain, P-N junction between N-type drain and P-type substrate is reverse biased, and due to negative voltage at the source, the P-N junction between the N-type source and P-type substrate is forward biased. Since reverse bias junction is in series with a forward bias junction between drain and source, there will be no current through this path. But when positive voltage is applied at gate terminal, minority carriers in P-type substrate are concentrated between drain and source and make a conducting channel. Hence, current starts flowing from drain to source. The conductivity of the channel depends on the amount of positive voltage applied at gate terminal. At zero gate voltage, there will be no current from drain to source, except negligible amount of constant saturation current due to minority carriers. But if there was a previously created N channel between drain and source, there would be a current through the channel due to applied voltage between the drain and source, even at zero gate voltage. In this case, the drain to source current can be made zero only when sufficient negative voltage is applied at gate terminal. The MOSFET fabricated by diffusing N channel between drain and source is called N-channel depletion MOSFET. The main advantage of this MOSFET is it can be used for controlling drain to source current, even for negative gate voltage. Now let us explain the basic working principle of this depletion MOSFET. As we see in MOSFET, there is a silicon dioxide insulation layer between metallic gate contact plate and substrate. That means there is a dielectric between conductor and semiconductor. Hence, this portion of the MOSFET behaves as a capacitor. If negative voltage is applied at gate terminal due to capacitor action, positive potential is accumulated on the N channel. Due to induced positive potential, majority carriers, that is free electrons in N channel, will be recombined, and hence there will be depletion of free electrons, and as a result, conductivity of the channel is reduced. If applied negative voltage at gate is sufficient enough, current through the channel from drain to source becomes zero. Now, if the gate voltage is gradually increased from this point to zero, the current through the channel is being increased accordingly, and even it increases for the gate voltage more than 0 volt. As the MOSFET works depending on depletion layer between drain and source, the MOSFET is referred as depletion MOSFET.